Thank you very much for the introduction. It's a great honor to be here and on this day in honor of Yvonne Choquet-Bruhat. As Genevieve has already pointed out, in Vienna we've had a workshop starting on Monday, so for the first 4 days of the week. Today's a public holiday in Austria in honor of Yvonne Choquet-Bruhat. And I would like to tell you a little bit about our workshop and about the recollections that that colleagues have had of Yvonne Choquet-Bruhat. So it turns out that Yvonne's autobiography has played a very important role for us because it's been a narrative through our workshop, and I would like to read at least 2 passages to you. Maybe more opportunities come up, but it actually turned out for us in Vienna that with every lecture given there was a passage in the autobiography that seemed just a perfect match for the occasion. So I would like, maybe I misunderstood earlier, but the fact that this autobiography came about seems to have been a joint effort. In the preface, however, it is the children who Yvonne gives full credit to. So she's writing in this autobiography, written on the occasion of my retirement from scientific work in the 90s, a mixed evocations of scientific ventures with stories of the near and distant travels they have occasioned, and of the scientists in all of these countries I came to know. I interspersed this account with that of events from my private life. The essential part of my life has been my 3 children, whose births range from 1950 to 1966. At their request, I have written these pages. So this autobiography is a work of love, and I do feel very much that the field of mathematical general relativity pioneered by Yvonne Choquet-Bruhat is also a work of love. So Yvonne built the house that is my home, my scientific home, and I guess the same is true for many, if not all of us here in this room, and that's an absolutely extraordinary accomplishment. So one of the speakers in the conference in Vienna, she pointed out that it also makes a great difference to her that, being a female mathematician, that she's working in a field that has been pioneered by a woman. And to that I would like to add, I think it makes a big difference to me too, and to all of us. So I would also like maybe staying with Vienna for a while. So I've brought a few mementos from Vienna, our conference in Vienna. So the first is, I guess, the cliche of every 100th birthday. So I've been looking around, about, things, birthday cards fit for 100th birthday, and it turns out there are very few, few that we found. But so here's to Yvonne in a few weeks. So it turns out we took the idea of a birthday party very seriously. There was some actual celebration and party hats. That is, there are the regular party hats that the guests are wearing, but this special hat, which is a crown, that would be for Yvonne to wear on her birthday. And it's also my great pleasure to present a card that all of the participants signed, also sometimes with short notes. Sergio, told you. please do. So it was a wonderful birthday conference in Vienna, so we've enjoyed it very much. Sergio? Sergio has a special place also on this card. Thank you so much. So I would like, before I get to my own talk, I would like to read another part of this autobiography to you. So there are several places, of course, where this institute is mentioned in the autobiography, and I would like to read to you the passage, it's 1.5 pages, about the hospitality at IHES. So I understand that the French, and I've been told that the original French version is vastly superior to the English translation. So I venture, since it's an international audience and also YouTube.
English translation is originally by Yvonne herself.
It was I will tell that to Piotr. So who maintains. But so I've enjoyed the English translation tremendously, and I think it should be required reading for everyone. So here's what Yvonne writes in her autobiography about the hospitality at IHES. On the occasion of my birthday colloquium, I much appreciated the nice cooperative atmosphere reigning at IHES, in welcoming premises favorable to work. Asbestos removal from Jussieu Towers had made me a physico-mathematician without an office nor internet means. Chatting with Jean-Pierre Bourguignon, I asked him if I could come occasionally to IHES to use the collective computer and printer. He answered yes, but added that I should have there a permanent base. Thibault found a solution by asking Pierre Cartier, retired from CERN S, to share with me his office. He probably couldn't refuse, but he accepted with good humor. I had known Pierre for more than 40 years and always had excellent relations with him. So I had the use of a coat rack and an armchair, as well as a piece of a table in the office, full of books and documents which had been occupied by Pierre for many years. It was perfect for me. The hospitality of IHES has changed my life in these last years. Thanks to it, I remained in contact with the science in progress and its propagators and perpetrators, who were and became my friends. Especially pleasant for me are my excellent weekly lunches in the cafeteria, with meals cooked by Patrick and always kindly being served first by Dominique and by other kind ladies when she retired. I used to sit at a middle-sized round table between Thibault d'Amour and another friendly scientist. It was often Laurent Laforgue, a physicist and a mathematician with the age of one or the other of my daughters. Interesting and varied exchanges with them and other guests stimulate my aging mind. Thibault continues to enlighten me with a commendable lot of goodwill on the rapid, often surprising development of our shared mistress, general relativity. The tea served in the common room by nice women is another occasion where interesting discussions were had, also with temporary visitors. The informatics service of l'IHES, François Bachelier and Karim Ben Abdallah, gave with great kindness precious help to the neophyte I was in the use of computer equipment and programs necessary to researchers, even theorists. The secretaries, especially Elisabeth Chassaron and Marie-Claude Verne, have always shown me a comforting sympathy. I passed the open door of Marie-Claude's office to reach mine, and she became a real friend. When our schedules permit, we chat while she drives me to the RER station. So it's very warm and also it is very funny. It's very much tongue-in-cheek in many places, and it seems some sense of humor is required in in particular in relation with l'Académie des Sciences. She describes in very humorous ways about her interactions and of course always with good humor and goodwill. So this having been said, I would like to begin with my own scientific talk. So I would like to tell you about a piece of mathematics, a piece of mathematical relativity that I've been working on intensively on and off for the past 12 years of my career on the canonical geometric structure of initial data for the Einstein equations. So a brief overview. I will start just with a very light-hearted presentation of optimal shapes, the optimal shapes that we'll be using in this talk. Then I would like to look at the positive mass theorem in its isoperimetric content. So the positive mass theorem is a fundamental theorem to test general relativity in the even though around as a conjecture from very early on, and in fact going back, as I've learned in the autobiography, to Einstein, but put together as a rigorous conjecture by Arnold, Desa, and Misner, is a theorem that relates a quantity that is derived from the Hamiltonian formalism of Arnold, Desa, and Misner, identify a mechanism that identifies this quantity as a natural candidate for what could be the mass of a space-time, or of initial data for the space-time development according to the Einstein equations, but to actually prove that it has the most obvious properties that you would expect of any mass, namely to be non-negative and identically equal to zero, if and only if one's initial data for the Minkowski space-time took a long time to transpire, and to recognize that this conjecture could be recast in purely geometric terms, which has led to the first proof of the positive mass conjecture in great generality by Schoen and Yao, has been a tremendous accomplishment that has in turn invigorated a lot of research in global analysis, the global calculus of variations. So then I would like to present a proof of a conjecture of Richard Schoen, who had been my own doctoral advisor. He and Xing-Tong Yao had been the ones who had proposed the first proof of the positive mass theorem, and this conjecture. Okay, that didn't happen to Thibaut.
Never went that far.
So I'd like to present to you a proof of this conjecture that's quite recent work, and it's in its recent repercussions, both in mathematical relativity and in pure geometry. So I'll start my presentation on optimal shapes a very long time ago. So you remember the question of isoperimetry. So if I give you a string, imagine a fence of a given length, I can, it's natural to pose oneself the question of the largest amount of area that you can put inside this amount of perimeter. And that's the original isoperimetric problem that, according to Virgil, was posed before Dido, Queen of Carthage, who was the first character, according to Virgil, to present the solution of this problem. So the largest amount of area that you can put in a given amount of string is the area of a disk whose radius, whose circumference is equal to the length of string. Of course, this question is one that you can make infinitely harder immediately when you are posing it not on a flat piece of land, but on a landscape with hills, for example, right? Just to give you an idea that the isoperimetric question is, historical and convincing as it seems, is one that you can ponder about and make infinitely harder by only a very slight variation. So that is the question of isoperimetry. You can put it, you can ask it to yourself in higher dimensions. So one dimension that is particularly important for me is dimension 3 for the Riemannian dimension of a 3 + 1 dimensional space-time, what is the largest amount of volume you might ask analogously then that you can put inside a closed surface of a given amount of surface area. Okay, so that's the higher dimensional analog. If you're in Euclidean space, in fact, any of the model geometries, be they spherical, hyperbolic, or Euclidean, the solution of this question, solutions of these questions have the highest amount of symmetry that you can expect. They are always geodesic spheres. Right, but again, actually, it turns out this isoperimetric question in higher dimensions, starting dimension 3, the full resolution of these conjectures is actually quite a recent accomplishment. It's around 100 years old that formal proofs have been presented to this question. So the isoperimetric question, along with the question of minimal surfaces, so the question of what is the least amount of area that you need to span a given boundary, those are foundational for what is called the geometric calculus of variations, which in the 20th century, in some way analogously to the development of the rigorous study of mathematical study of the Einstein equations, has seen an unprecedented and extremely successful development. So the second question is the one of minimal surfaces, and historically it goes by the name of Plateau's problem. So if you want to put it playfully, again, it's something that we've all arrived at. Remember taking bubble baths? Maybe you still do that on occasions. I know I like them. So when you take a bubble bath and you form you have a piece of wire on you, and you form it into a closed curve, right? And bend it any odd way. You may observe that when you dip it into soap solution and pull it out, a film will be formed that spans this contour, and you can pop your soap film and repeat the experiment, and chances are you will pull out the same shape again out of your bubble bath for the same contour. So it's reasonable to expect that these surfaces, these soap films, are special in a substantial way, and indeed they solve the problem of least area. So these soap films, at least ideally, they are those surfaces that span among all surfaces with the given boundary, that span the given boundary with the least amount of area possible. So all of these questions sound a little bit like extremal value problems that we solve in high school already. So the big difference being that these problems are infinite dimensional extremal value problems, owing to the fact that the space of possible surfaces that there are to fill in a given boundary is not described by a finite dimensional space, but it is highly infinite dimensional. Okay, so but it turns out, and this is in fact the subject of one of the first 2 Fields medals awarded in mathematics. So that's the Fields medal awarded to Jesse Douglas in 1936 for the solution, the first rigorous mathematical model of soap films, including a proof of existence. So he proved what every child is observing, that every closed curve in Euclidean free space is spanned by a surface of least area. So this is a spectacular breakthrough, but it turns out it's by far not the end of this story. So it's the field of geometric measure theory that needed to be developed to look at this question in full generality, and there's still many open questions.
And here minimal means extremal? Minimal
means extremal here, but that's just for the sake of argument and to cut it short. So minimal I will use in analogy. I will use to mean area minimizing. So minimal is in fact just if you're honest about it, is just the name for the critical point condition.
But it can't be a maximum, right?
Hardly, because the maximum is you can always you can always go overboard with your surfaces, but saddle points, for example, it's important to study. But the index is away from least area surfaces, not from maximum area surfaces. So, but maybe let me also say that minimal surfaces are very closely related, as mathematical models to how we think of apparent horizons in mathematical relativity. So apparent horizons in initial data satisfy an equation of prescribed mean curvature. So the mean curvature of a two-dimensional surface in three-dimensional initial data is prescribed as the trace of the extrinsic second fundamental form along this surface. So be one of the two expansions equal to 0. That's an equation that is mathematically closely related to the minimal surface equation. The big difference being that the apparent horizon equation in full generality is not one that arises variationally. So in fact, it's so another part of my research life to bring this analogy between minimal surfaces and apparent horizons closer together, but it's not the subject of this talk. So just a few reminders to set the stage, lessons from Carl Friedrich Gauss. So Carl Friedrich Gauss observed fundamentally that when you have a curved surface, such as the surface of the Earth, then all the linear scales that you find on maps in a high school atlas, for example, are a cheat, right? You cannot make a map of a curved surfaces where all real-world distances appear scaled by the same scale factor independent of position. So all these distances appear distorted, not in a linear way, but in a non-linear way. Geodesics, so the shortest ways of getting from one point to another, are not straight lines. Are not straight lines. And as a takeaway, if you've never thought about this before, there's another way to capture, and this is going back to an observation of Gauss, this insight already, that you can also capture curvature on the level of the isoperimetric problem. So it turns out when you ask yourself, the isoperimetric question, what is the shortest, what is the largest amount of area that you can put into, let's say, a short amount of string on a curved surface, when that surface is positively curved, it will be slightly more than the amount of area that you can enclose in Euclidean space, right? Slightly more than what you get in Euclidean space. And you can make this relationship more precise. In fact, when you look at the volume of small geodesic balls, so you take a point in your Riemannian manifold and a small radius r, and when you compute the radius of this, the volume of the corresponding geodesic ball, and subtract from it this quantity, I'll comment on it in a moment, and Taylor expand, on the right-hand side you will see the scalar curvature of the Riemannian manifold at the point, times r to the 5 followed by lower order terms or higher order terms. So notice when the scalar curvature is positive, this quantity on the right-hand side here is also a positive quantity. Let's look at this left-hand side for a moment. So the area, I can not only compute the volume of a geodesic ball, I can also compute the area of a geodesic sphere. Think for a moment, you recognize this quantity. So I give you a given amount of area and I form this quantity. It's exactly the volume of a Euclidean ball whose surface area is given by this amount of area. So what I'm computing, what I'm looking at on the left-hand side is the volume of the geodesic ball, from which I subtract how much volume in Euclidean space I could enclose with the same amount of surface area. And what this is telling you is that it's called the isoperimetric deficit, when you're at a point of positive scalar curvature, you can pack slightly more volume into the same amount of geodesic, of area of geodesic spheres than you could in Euclidean space. So let's take all of this now to general Riemannian free manifolds. In fact, asymptotically flat Riemannian free manifolds. Suppose we have a Riemannian free manifold. What makes it asymptotically flat? Well, it's asymptotically flat if it approaches Euclidean space at infinity, meaning that if you subtract the compact set from your Riemannian free manifold, the residual space is diffeomorphic to the complement of a ball in Euclidean space. And when you look at the Riemannian metric in this asymptotically flat coordinates, as they are called, then it oscillates to the Euclidean metric up to lower order terms. So that's it. That's what makes a Riemannian manifold, a three manifold, asymptotically flat, and somehow the importance of these asymptotically flat Riemannian manifolds to model isolated gravitational or initial data for isolated gravitational systems is known, of course, to all of you. So we also require that scalar curvature be an integrable function. Notice that doesn't follow from the decay assumptions by themselves. And if M should have a boundary, then we require that it be an outermost minimal surface. So that is the apparent horizon condition. So in the setting of the Riemannian positive mass theorem, and then more importantly the Riemannian Penrose inequality, these results hold when the boundary is an outermost minimal surface, so a closed minimal surface such that there are no larger minimal surfaces enclosing them in the manifold. So what is now the content of the positive mass theorem? So we assume that we have such asymptotically flat Riemannian three manifold, and we also assume that the scalar curvature is non-negative. So that would be true for maximal initial datum so if Mg arises as a space-like slice of a space-time satisfying the dominant energy condition that sits inside the space-time as a maximal surface. So in Lorentz geometry, the analog of minimal surfaces are maximal surfaces. So space-time mean curvature equal to 0. Then the scalar curvature is non-negative, and then you can look in these asymptotically flat coordinates at this quantity called the ADM mass after Arnovit, Desa, and Misner. So it's formed as a limit of flux integrals, of quantities that involve first derivatives of the matrix. So it doesn't look very geometric at all for several reasons. The first derivatives of the metric for one, and then also the apparent dependence on the choice of asymptotically flat coordinates to start with. But it turns out, and this was shown by established and put on firm ground by Robert Bartnik, that indeed this ADM mass is an intrinsic quantity of any asymptotically flat Riemannian manifold with integrable scalar curvature. And now the question, the fundamental question in the development of mathematical relativity, the positive mass theorem, is that in the case where the scalar curvature is non-negative, the ADM mass is a non-negative quantity, and equality holds only if you are in Euclidean space. So this was proven by Schoen and Yao, appeared in a paper published in Communications in Mathematical Physics in 1979. Very shortly after, an alternative proof was given by Edward Witten, based on the Dirac equation for spinor fields. What I want to say is that by now we have several proofs of the positive mass theorem. For example, the one coming out of the resolution of the Riemannian-Penrose inequality by Huisken and Illmannen, or the recent work of Lorenzo Mazzieri, for example. So lots of contributions. So they not only, so the reason I'm emphasizing the role of Schoen and Yao here is for one, they were the first ones, and the other reason is because their proof, the way they went about proving this theorem is important for me. So I would like to give you a small taste of this, proof of the positive mass theorem after Schoen and Yao. That is purely geometric, so you know, and that had preceded the proof of the positive mass theorem, is the following resolution of Jarok's conjecture. So it's a proof of the fact that when you have a Riemannian free manifold that has positive scalar curvature, it couldn't possibly admit a torus which has least area inside of its homology class. So the way to you know, to think of the setting of this theorem, it's best to think of S2 cross R. I'm sorry, S2 cross S1. So a standard 3 torus that would have of course, non-negative scalar curvature, and you can take any of these. I'm sorry, actually. Oh, that was very silly. So these 3 torus. So S1 cross S1. So you can take any one of these cross-sectional tori that are forming out the torus, and you can ask in their homology class what is the least area torus in this manifold. And what Schoen and Yao observed is that when the scalar curvature of this manifold is positive, there is no least area such torus, and you know, seeing that you can use the apparatus of geometric measure theory to prove the existence of such tori in such a topological configuration, you conclude that such a torus cannot carry a metric of positive scalar curvature. So let me quickly show you how this is proven. So as indicated, it's you know, when you have okay, let's just assume we have a two-sided closed and area minimizing surface sigma contained in a Riemannian free manifold. So because it is area minimizing, it satisfies the first and second derivative test for least area, meaning that when you perturb the surface in any direction, and you consider the family of surfaces you know, generated by this perturbation, if you evaluate the area functional along this family coming from this perturbation, then the derivative at t is equal to 0 of the area functional should be 0, because it's a critical point, and the second derivative should be non-negative. So what this amounts to in geometric terms is the condition that the surface must have vanishing mean curvature, and the second derivative test for the area functional for minimal surfaces, so surfaces whose mean curvature vanishes, is this variational inequality on sigma. So now we use Schoen and Yao used a special variation, namely the one coming from perturbing the surface, this least area surface, by perturbing it with the same speed, constant speed in every direction. So it's passing, you know, it's looking at the torus within a family of parallel surfaces. In this case, this function u that generates the variation in normal direction is equal to 1. So what comes out of this second derivative test is this variational inequality, where a of sigma is the squared. This is the sum of principal curvatures of the surface squared, and Ricci is evaluated in the normal direction. But this turns out to contradict the Gauss-Bonnet theorem if the surface sigma is has the topology of a torus. And why is that? So notice the scalar curvature is something we assume to be positive. The scalar curvature on the 2 surface can be expressed by the Gauss-Bonnet formula by this expression here. So 2 times the intrinsic Gauss curvature minus the mean curvature squared, so mean curvature is 0, plus sum of squares of principal curvatures, plus twice the Ricci tensor. So if you integrate this Gauss equation, you get a positive quantity is equal to, now by the Gauss-Bonnet theorem, 0, 0, that quantity plus twice that quantity. So that is bigger than 0. So if you add, you know, this quantity, the integral of this quantity, which is non-negative, to said expression, you would find that this integral here should be a positive quantity. And that's your patent contradiction. So this is an important part of the argument of the proof of the positive mass theorem after Schoen and Yau, the minimal surface proof. So I would now like, and I will come back to this, I would now like to present a synthetic view of the isoperimetric problem in Riemannian 3 manifolds and the notion of mass in mathematical relativity. And I will present it in terms of a theorem that is joint work with my first PhD student, Chodosh, Yu Guangxi, and Haobin Yu from Peking University, and it appeared a few years ago. So assume we have an asymptotically flat Riemannian 3 manifold that has non-negative scalar curvature but positive mass. So it's not isometric to Euclidean R3. So let me say something maybe in advance before I complete the statement of this theorem, that when you look at the isoperimetric problem in flat R3, it has many solutions. So if you have one solution of the isoperimetric problem in R3, you know, even if you didn't know it was a sphere, you would have many of them, right? Because you can move them around by all the isometries of Euclidean space. It wouldn't change area or surface area, right? So the solutions of the isoperimetric problem in Euclidean space are not unique. However, when you are asymptotically flat with non-negative scalar curvature, but not Euclidean space, the content of this theorem is that if you give yourself any large amount of area A, then the isoperimetric problem for this large amount of area, meaning the question or the search for that region in your Riemannian manifold whose surface area is given by A, which contains the last amount of volume possible, has a solution. So it's not clear to start with, you know, from the outset, even that, you know, isoperimetric questions have solutions, but it turns out in this setting, you always have a solution. And it turns out that if A is sufficiently large, that solution is unique. So the fact that you have positive mass leads ensures that these large isoperimetric surfaces are unique. And in fact, they're not only unique, the boundaries of these solutions of the isoperimetric problem for large areas, they form a foliation of the complement of a compact subset of your MG. I'll explain a little more about this in just a moment. So this settles an old question by Gerhard Huisken, going back to his work on defining canonical center of mass and canonical spherical coordinate system in isolated gravitational systems with Yau in the early 90s, which had been for asymptotically Schwarzschild manifolds. So notice also this is a theorem that is very general asymptotically flat initial data. Many people have contributed to this problem in a substantial way. I would, you can read their names here, and I wish I could tell you more about each and every one of these contributions, but time does not permit. But let me emphasize the work of Hugh Bray and his work on the Penrose inequality, who has solved the isoparametric problem in Schwarzschild, Schwarzschild initial data, which the solutions in isotropic coordinates are given by the centered coordinate spheres. You would expect it, but it turns out there maybe also something that I would like, this is important to be aware of. When you look at all the geometries where you know exactly what isoparametric regions look like, it turns out to be a very short list. And this is the first global result in this direction that doesn't require any precise symmetries at all in the large scale setting. So this is what these large isoparametric surfaces look like. So this is a picture of a tree that has sadly been cut. So think of the rings of the tree that form. They are not circular, right? And the closer to the center you are, the more distorted they might appear. But so what happens in this initial data is when you look at these unique solutions of the large of the isoparametric problem for large volumes, then these solutions they are actually nested, and the boundaries of these isoparametric surfaces they form a foliation. And it also turns out that these isoparametric surfaces, if you look at them at large scales, geometrically they converge to centered coordinate spheres. So these isoparametric regions, they detect, I'm saying here, the mass and the center of mass. I don't want to focus on the center on mass, but on the ADM mass. So it turns out, so omega A is the unique isoparametric region with boundary area A. If you look at its isoparametric deficit, so if you consider how much volume this region contains when compared with the volume of a Euclidean ball with the same surface area, A, then it turns out that when you scale to the scale of area, this recovers exactly the ADM mass. And if you think about what this means in relation with the positive mass theorem, it's telling you that when the mass is positive, so when you're not flat R3, you can in such initial data, the volume is always much greater than in Euclidean space. So from an isoparametric standpoint, these geometries are superior to Euclidean space. So a closely related conjecture of so this is somehow this idea of recasting the ADM mass geometrically. This is a vision of Gerhard Huisken, and also these result here very emphatically realizes this stream as a theorem. So now I would like to talk about a closely related conjecture of Rik-Schoen. So closely related not only thematically, but also because it's a very important ingredient of the proof. Again, I would like to present this conjecture as a theorem that I've established together with Otis Chodosh, and the corresponding question goes back already to the very beginning of the positive mass theorem as a theorem. So suppose you have an asymptotically flat Riemannian free manifold with non-negative scalar curvature. If there exists a complete unbounded least area surface sigma in M, then this theorem asserts the asymptotically flat Riemannian free manifold is actually flat Euclidean space. So So, you know, this condition here, it's like a mouthful. You can imagine, you know, remember our bubble baths? So, you know, this is one way of obtaining minimal surfaces as solutions of the plateau problem. Now think of, you know, the boundary that we use to create these solutions of the plateau problem is, let's send them to infinity, and let's hope there will be something left in the limit. So it turns out you can take limits of minimal surface. Minimal surfaces are very tame geometrically. They satisfy the best possible kinds of a priori estimates. So if anything is left in the limit, it will be an unbounded area minimizing surface. So it doesn't have boundary itself anymore. It will be a complete area minimizing boundary. So what does that mean when you have a surface without boundary? What does it mean for it to be area minimizing? It means that when you take any compact perturbation of that surface, you know, and look at its area in an open subset that contains the perturbation, then area is increased. Or more precisely, not decreased. Okay, so here's a picture of what I just said. So I, you know, again, I'm beginning now to use these analogies. Behind these analogies is a lot of machinery. But let's think of them as infinitely extended subforms for the sake of argument. Maybe also something that I'm already, you know, to build this relationship to what I had said earlier. So I've described to you now one way of potentially obtaining such infinitely extended area minimizing surfaces that don't have boundary anymore. Conceivably, there's another way of obtaining such surfaces. So area solutions of the isoperimetric problem. I will give you a very naive example, but it turns out this naive example is maybe not so naive after all. In Euclidean space, let's look at spheres that are tangent to this plane and touch at this point. And let's take their radii to infinity. Okay, the geometric limit of these spheres, right, will be this plane, right? And it turns out that's all that can happen. So when you have isoperimetric regions whose volume or whose area is divergent, if there is a limit, then it has to be an area minimizing surface without boundary that remains. So isoperimetric surfaces have have constant mean curvature. Minimal surfaces have zero mean curvature. So, you know, that's a fit. And maybe what I just said is not exactly true, but it's close enough. Okay, so this is what it means to have an infinitely extended subform in MG. So here's a slightly shaded region and a compact perturbation. So if I have such an infinitely extended area minimizing surface and compact perturbation, then I'm not decreasing area ever, by definition. So there are three ingredients. So I would like to take you briefly through the proof of this argument because I love it very much. And it's a shooting method, turns out, for minimal surfaces. So the three ingredients are, so the first thing is that the plateau problem always has a solution. So more precisely, if you are inside of a mean convex region, so a top-dimensional submanifold whose boundary is such that you know, when you're perturbing outward, you are increasing area, and if you take any you know, wireframe that lies on the boundary of such a region, you can always find inside of that region an area minimizing surface that spans this boundary with the least amount of area possible. So that's solving the plateau problem. That's always possible. The second ingredient is the fact that area minimizing surfaces satisfy great a priori estimates. It's you know, as in PDEs, when you you know, when elliptic regularity takes over and you know you've made it. So soap films are tame objects. And the third ingredient is related to this taste of the proof of the positive mass theorem that I've given to you. So if you have, it turns out, and this is something I'm asking you to believe me, this is something also proven by Rick Schoen and Doris Fischer-Kolbry, I should say in this form, in this form or another, so the couple of papers that are working together here in this context. If you have an unbounded least area surface along which the ambient scalar curvature is non-negative, right? If you have an unbounded, such an infinitely extended soap film, and the scalar curvature along it is non-negative. There's a reason I'm you know, saying just along it, okay? Because it might be negative in other places for the purpose of this theorem. Then, so the proof of this theorem is on the surface. It's not global within the initial data set. Then the surface sigma turns out to be totally geodesic, so all the principal curvatures are equal to 0. It's intrinsically flat, and also the ambient scalar curvature, the ambient full curvature tensor vanishes along such a surface. So if you have an infinitely extended soap film, then it really looks like you know, a page in a perfectly pressed book. Let's call it flat. So how does the proof go? Suppose we have one of these infinitely extended soap films sigma. By the ingredient 3, this surface sigma here is intrinsically flat. It has second fundamental. All the principal curvatures are 0. It's really, you know, sitting there and is very, very flat. So I would love to find another such surface sigma that cuts through a point P that doesn't lie on the surface. So what I'm trying to do is I'm trying to build a foliation of Mg by surfaces that are infinitely extended soap films and that do not intersect one another. Okay, so how could I do that? So I have Mg, the scalar curvature is assumed to be non-negative, and here this point P through which I would like to build another such surface. So and here's what we do. We take a geodesic bore. It doesn't have to be a geodesic bore, but let's say P is close to sigma, and we take a bore, a red bore, geodesic, that intersects with sigma. P is the center, and we perturb the metric in this geodesic bore such that you know, inside the bore all distances are decreased. Okay, the metric goes down slightly. We also assume that you know, under this perturbation, this surface sigma here is a minimal surface, right? And now we assume that with respect to the region above, with this new metric, the surface sigma is a mean convex surface. So again, meaning that if, you know, in the red bore you push sigma down slightly, you are increasing its area. Again, the area decreases. And there's a third thing that we can arrange, namely we can arrange that the scalar curvature, which was non-negative on all of M, in this perturbation, in an annulus that intersects sigma, but does not reach, you know, towards P, is strictly positive. So it's not difficult to show how that you can form such a perturbation, but these are the 3 crucial properties that you need to ensure for the purpose of the proof. So mean convex region, sigma becomes a mean convex region, the distances decrease inside of through the perturbation, and the scalar curvature becomes positive in an annulus that intersects with sigma. So now what we do is we take a very large coordinate sphere in our asymptotically flat manifold, and we look at the one-dimensional closed curve that is the intersection with our infinitely extended soap film. And then we Okay, and what I do is I'm going to solve the plateau problem for this intersecting curve, this one-dimensional curve, in this mean convex region with respect to the perturbed metric g of t. So let's say the solution is rho sigma of t. So a new area minimizing surface, this time with boundary, right, and the boundary is the intersection of sigma with this large geodesic coordinate sphere. So now I claim that okay, so this is still, you know, sigma rho of t. I claim that this least area surface that I found by solving the plateau problem must intersect the red ball where we've perturbed the metric. It must intersect the red ball where we've perturbed the metric. That's why I'm saying here this is not the sigma rho of t that is a minimizer solution of the plateau problem. So suppose our least area surface looked like this and were disjoint from this red region, but then consider when you look at the area of sigma, the original surface sigma, inside this big region here, so that's the area of this region here, with respect to gt, well, that is less than the original area of sigma with respect to the metric g, because in the red ball we've decreased all lengths and thus also area, so strictly less. So, and then by construction of sigma rho of t, this is not the construction of sigma rho of t, this is the minimizing property of sigma. This would be less than or equal to the area of this surface here, right? Because sigma is area minimizing with respect to g. But now, because sigma rho of t does not intersect with the red ball where we've decreased, where we've changed the metric, this is equal to the gt area of this surface that I claim could not possibly be our solution of the plateau problem. So now when you look at this, you obtain a contradiction, right? Because this string of inequality says that sigma rho of t is not minimizing with that boundary with respect to g of t. Sigma is a fair competitor, permissible competitor, and thus better. So the surface has to go through this red ball where we've done where we've made the perturbation. So the next thing I claim is that the surface sigma rho of t for rho very large has to intersect the green ball. Okay, and remember the green ball is is the complement of the annulus in the red ball where we've changed the metric. So why does the surface sigma rho of t have to intersect this small green ball for sufficiently large rho? Well, suppose it didn't, right? For any sequence of rho I tending to infinity. Well, if we had a sequence of such surfaces sigma rho of t, all intersecting the red ball, tending to infinity, and all of them do not intersect the green ball, then because soap films are tame, we can pass to a limit, and this limiting surface will be an infinitely extended soap film in mg with respect to the metric g of t, this perturbed metric. Because it doesn't intersect the one part of the manifold where the scalar curvature is possibly negative, right? It satisfies the conditions of this ingredient 3. This was a mistake, I'm sorry. This ingredient 3, so I claim it would satisfy the conditions of this gradient 3, and the conclusion is that this surface would be totally geodesic, blah, 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 and the scalar curvature vanishes along this surface. But this cannot happen, right? Because we've shown that all of these surfaces pass through the red region, pass through the orange annulus where the scalar curvature is bigger than 0. So all of these surfaces sigma rho of t for rho large enough pass through this, this green region. Okay. So now what I do is we take the limit of these surfaces that we found for radii rho I tending to infinity, and at the same time we take the parameter of the perturbation of the metric to 0, so that the Riemannian matrix approach smoothly the Euclidean metric, and we find a limiting such infinitely extended subform, of which we now know that it passes through this ball, through this green ball, right? That was exactly the point. It cannot, so the enemy in this construction is, by the way, maybe I should point this out more clearly, is that, such surfaces here, that the limit disappears. This would be a disaster, but conceivable to happen, or that they converge back to the original sigma, meaning that we're back to where we started, right? But by combining these two arguments, we show that neither is the case. So we obtain another infinitely extended subform, and I've told you all these infinitely extended subforms are flat. So they really look like this, right? You can pass this to a you can iterate this construction and use it to show that you can actually foliate all of MG by such flat surfaces. Okay. And by which the proof is finished. So you have to be flat R3 to start with. So this technique that we've developed here, we've been able to use it to answer another long-standing purely geometric question. So this is, goes back to the origin of these conjectures is when it was believed that using minimal surface techniques one could classify all Riemannian free manifolds, this is a large program back in the day, and one of a fundamental conjecture in this question in this context is that if you have a complete Riemannian free manifold with non-negative scalar curvature, what can you say about such manifolds when they contain an area minimizing cylinder? So that's an unbounded surface, a surface with a boundary properly embedded, an area minimizing with respect to all, absolutely area minimizing with respect to all perturbations. And a geometric repercussion of the proof is that this can only happen when the manifold, your free manifold, is actually a cover of the standard cylinder S1 cross R2. Okay, so this is a purely geometric result. In the last few moments, I would like to just bring some sensitivity to why these problems are subtle. So in 2014, Alessandro Carlotto and Rick Schoen, they gave a construction, a huge accomplishment. So they constructed initial data on R3 where so this is asymptotically flat initial data with good decay, such that the scalar curvature of G is actually identically equal to 0, and such that down here the metric, so in the lower half space, the metric is isometric to the Euclidean metric. So asymptotically flat initial data that contains isometrically a Euclidean half space. So it's odd, right? Because it's somehow there's no somehow the rotational symmetry of Schwarzschild, for example, right? There's none of that. There's just one piece that looks exactly like Euclidean space. So notice that the theorem I presented to you earlier, this result about large isoperimetric regions, applies to such initial data sets. You know, and concludes, right? Notice this is Euclidean space, right? You have lots of stable CMC surfaces in Euclidean space, right? That you simply transplant from Euclidean space. But it turns out you cannot transplant them to such manifolds as isoperimetric surfaces, right? Because the solutions of the isoperimetric surface of this problem, they look like this. Right? They necessarily encompass a large part of the Euclidean region and a large part of the region where you're not isometric to Euclidean space. So this doesn't pan out. So notice specifically also this conjecture that I've just shown you about, when you have an infinitely extended soap film, then you have to be isometric to Euclidean space, that when you look at these Euclidean planes here where the metric is isometric to Euclidean space, they could not possibly be area minimizing. If they were area minimizing, then the whole thing would have to be Euclidean space. Is this okay? And now it turns out there's a bit of a shock when you go to one dimension higher. So these Carlotto-Schoen examples, you can do them just the same in higher dimensions. So replace R3 by R4. You have a Euclidean half space, zero scalar curvature, not isometric to Euclidean space, so positive mass. So, and it turns out in these examples, we've been able to prove that these Euclidean planes here, they are area minimizing. It is very odd, right? And the reason, actually the reason is a bit complicated, but it turns out that this is a very special feature when you pass from dimension 3 to dimension 4. No, okay, well, it's complicated. But there's something that happens and it's subtle and it changes the full picture. So this is joint work with my brilliant postdoc Thomas Koerber, that this conjecture of Rik-Schoens does not hold in dimension greater or equal than 4, but is so often there's a counterpart to this, namely that the result that to us was essential to prove this classification of large isoperimetric regions in three-dimensional asymptotically flat manifolds. That part of Schoen's conjecture is true. So, I'm putting it here as a theorem. So if you have an asymptotically flat Riemannian manifold with non-negative scalar curvature and the dimension is between 4 and 7, then it is true that if you have an infinitely extended soap film that arises as a limit, of isoperimetric regions, then if this is possible, then you have to be flat R'ing. And that means, right, when you try and understand, this corresponds to a statement on a PDE level, meaning that if you are trying to study large isoperimetric regions in such surfaces, the thing that you might most worry about is that these large isoperimetric regions, they cut, their surfaces cut through the part of the manifold that is far from Euclidean space. And this positive result rules out exactly this scenario. So either large isoperimetric regions are far out altogether, or they consume the center of the manifold. And with that, I thank you very much for your attention. Thank you for having me.
Thank you very much for this very nice talk. So are there any questions? See?
So in the theorem, the first theorem of you that you presented with several people of 2019, I think, I understand why with the formula you gave, why this family of solution to the asymptotic problems, they capture the mass, but why do they capture the center of mass?
So this is related to this program of Huisken and that so their program is actually not for isoperimetric regions, it's for stable CMC surfaces, and it's the question of when you have a large stable CMC surface, so a surface that passes first and second derivative test for being an isoperimetric region of large volume, is to characterize such surfaces, to prove that they are close perturbations of coordinate spheres, and to show that when you have these special perturbations of large centered coordinate spheres, when you form in the asymptotically flat chart their center of mass, the barycentric center of mass, that these quantities converge as you move outward along the foliation. So it turns out this program is this is also there's a long open conjecture of Huisken and that this should be possible. It was disproven by Simon Brändler and myself, I believe in 2013. But again, there is a large part of this result is true and turns out to be true in great generality, which is a result of Otis Chodosh and mine. So essentially the conjecture is it has a lot of truth in it, and these large. So one thing that one needs to show along the way, and again there are many partial results. The most definite ones. This is a recent and joint work with Otis Chodosh and Thomas Koerber, that even if your manifold satisfies very weak asymptotics, as long as it isn't Euclidean space, you can find these foliations at infinity, and then showing that, and then you need to connect. Of course, you would like to think that these large surfaces are being stable critical points and unique within a large class of surfaces as stable critical points of the isoperimetric problem, that they are actually the solutions of the isoperimetric problem, and that turns out to be essentially true fully true in 3 dimensions. And that's why this result holds. So if you take these large solutions of the isoperimetric problem, their boundaries are part of this. So this foliation that their boundaries form coincides with the foliation by large stable CMC surfaces whose barycentric centers of mass converge to the ADM center of mass. If you have additional assumptions on scalar curvature, so this is something that Schoen and Huisken unfortunately missed in their paper. So you need, for the convergence of these centers of masses, you need additional assumptions on the scalar curvature. It needs to say, if you have Reggie Teitelbaum, for example, on the level of scalar curvature, it's true. But if you don't, then center of mass is elusive and may not be well defined.
Can you remind us of what happens to the plateau problem in minimal surfaces in 8 dimensions or higher?
Well,
I mean, whatever, the plateau or whatever.
Yeah. So it's a standard piece of geometric.
Becomes very.
I mean, you always have solutions. I mean, you always have weak solutions, if you will, and there's a remarkable partial regularity theory for these solutions, stating that away from a closed singular set of codimension 7, they are smooth.
Yeah, sorry.
Smooth. So away from a codimension 7 set, these weak solutions of the plateau problem are smooth. So, for example, when you look, when the ambient manifold is 8-dimensional, the singularities that you might see are in fact, they form a discrete set. They cannot even accumulate. And then co-dimension 2, 1 dimension up.
Are there analogous results for Lorentzian manifolds?
No, no. No. I mean, one might, of course. So this is, one might ask, what is the most natural way to fill in a codimension 2 surface in a space-time by, you know, if it's possible to fill it in with a 3-dimensional space-like hypersurface. It's a very natural question to ask. What is and actually a very good question to ask. So thank you for bringing it up. What is you know, what is what would be the least volume way to fill it in? I don't think there are positive results in this direction, but I think it's it would be really fun to study that.
Even if they are asymptotically flat, this changes nothing.
One would think, but maybe it's not clear. Well, then you could also. I mean, it's also the question, right? When you have which are canonical space. Well, but we've learned also from the work of Sergio and Jeremy, finding somehow. You know, finding large canonical surfaces in space-times. So for you, they are satisfy the apparent horizon condition, or if constant expansions both ways. So I like these questions very much, right? These surfaces are useful, and you demonstrate very impressively why. But somehow the question, what are the most natural surfaces, most appealing surfaces that end up having the best properties I find a very nice set of questions, and I think it has not been. I think there's a lot of work to be done. Thank you for the question.
Other questions? Let's Michel again.